Okay, so this is the second part of my permutations day 2. I had to stop because I was running over 15 minutes, and I think that's all YouTube will give me, and I'm probably going to post it on there just in case other people want to use it. I figure if I'm making it, people might as well use it, even if it's 6 of you. It's a good thing that I took a break anyways, though, because these next 3 questions are going to get tough. Like, 15 is a beast. 15 is probably harder than what your teacher would assign you, but just in case. Some teachers are mean, like apparently I am. How many permutations of the number 1, 2, 3, 4, 5 have 4 and 5 separated by exactly? Oh, okay, this is a cool question. So this question is separated by exactly. So instead of doing just adjacent questions, they also can separate them by exactly some number. So n is equal to, so 1, 2, 3, 4, 5, so we're dealing with 5. It's saying how many permutations of the numbers, so k is equal to 5 as well, it's a full perm. And they want 4 and 5 separated by exactly one other number, so 5. So let's have a look at these seats here. So we've got these 5 seats and we need to separate it by one number. So let's put the 4 down there and the 5 down there. So they are separated now by one number. So there's 1, 4 and there's 1, 5. And then I'm going to drop in some of the other numbers from the bag. So there were 5 numbers in the bag, 2 are placed down, so now I have 3, 2, 1. I fill in my randoms. And now I have to look at places. So they could be there, 1, 2, or 3 different places. So I'm going to times by 3 for the places, and then I'm going to times by 2 for the switch. So this could be in 3 places, and remember that it's the switch, because they have to be separated by exactly. So it could be 4 there or 5 there. They could switch. So that's the times 2 for the switch. And there's times 3 because they could be in 3 different places. So this ends up being 3 factorial times 6. B. Actually, you know what? I'm going to do B over here. I need to save space for that last B's question. Separated by exactly 2 numbers. 1, 2, 3, 4, 5. So there's 5 numbers in total, 5 seats. Going to drop the 4, it's separated by 2 numbers from the 5, so there's the 4 and the 5, there's only one of them. Go back to the bag, drop the 3, 2, 1, multiply this time. How many places we got? Well, there's just 1 and 2. There's 2 different places it could be in, and times 2 for the switch. So this one is going to be equal to 3 factorial times 4, and lastly C separated by 3 numbers, 1, 2, 3, 4, 5. So drop the 4, drop the 5, there's one of each of those, drop our randoms, 3, 2, 1. Times, well, there's only one place they could be in, so all I have to do is times for the switch. So this one's going to be equal to 3 factorial times 2. So that is how you buy specific numbers. So if it says the 2 numbers are separated, though, that's a totally different question. So if they're adjacent, they're beside. If they're separated, then they're not adjacent. We'll get to a question like that at some point. But this is a good question to know. So this is how you do separated by exactly. Let's go to 14. Okay, so 14. How many permutations of the numbers 1, 2, 3, 4, 5, 6, 7, 8, taken 5 at a time? So n's equal to 8. We are only taking 5 at a time, so k is equal to 5. Have the 7 and the 8 in adjacents. Okay, so this is a good question. It's an adjacent when it's not a full permutation. And you'll notice something a little bit different happens here. First of all, I'm going to put the 7 and the 8 adjacent. So 7 and the 8. So first of all, they have to be in the word. They have to be in the perm. We're dealing with numbers. They don't make words. So they have to be in the permutation. 7 and 8 go down there. I'm going to join the seat again. Just mine. So we join the seat. And now I fill in the rest of them. So the randoms. I've dropped a 7 and 8 out of a bag of 8 numbers. So there is 6, 5, 4. It doesn't count all the way down because it's not a full perm. And then we go back and look at the number of places. Now, normally when it is a full perm, this number would be 7, but that doesn't happen when it's not a full permutation. Look at those 2 spots. So that could be in 1, 2, 3, 4. So in this case, they are only in 4 places. So this is the places, and still times 2. Whoops, I'm supposed to circle switch. Times 2 for the switch. So this ends up being 6p3 times 4 times 2, so we'll call that 6p3 times 8. Cool. So this is important. This is adjacent, not full perm. Or I guess I could call it adjacent B. Have the 7 and 8 separated by exactly one number. Okay, we just did this exactly one number thing. So 1, 2, 3, 4, 5. It's still 8 numbers, taking 5 of them. We're going to put the 7. If we drop these two numbers, there is 6. And then 5, 4. Counting down. Repetition is not allowed on a perm. Now, multiply by the number of places. 1, 2, 3 places. Multiply by the switch, because they're still separated by 1 if it was 8, 7 instead of 7, 8. So times 2. Ooh, look what happened here. So, simplify this. 6, 5, 4, 3, 2, 1. It's 1, 2, 3, 4, 5, counting down. But it also is 6 factorial, because really if you wanted to times by 1, you could, and now we've got the full countdown. Cool? All right. So that is separated by exactly with a not full perm. Pretty much exactly. Now, 15. Here we go. How many permutations of the letters A, B, C, D, E, F, G? 1, 2, 3, 4, 5, 6, 7. So n's equal to 7. And they're looking at full perms, so k is equal to 7. Now, do you realize why this is a full perm again? So whenever it says how many permutations of the letters, if it doesn't tell you taken so many at a time, then it is a full perm. So this is a full perm. And have the A and B are adjacent, and the C and D are adjacent. So this gets tough. 1, 2, 3. Now I'm going to put down the A and the B and the C and the D. We're going to make them adjacent. I'm going to join these two and join these two. Now, after that, so my 3, 2, 1. And then how many places can these be in? Well, that gets really hard to tell. So if you want to try to move these things all around and see how many places they could all be in, it's pretty crazy. So what we do instead is I'm just going to permeate these 5 things. So because I have attached the A and the B, so these are locked, and I've attached the C and the D, so these are locked, now I can just permeate these 5 things. Now this only works with a full permutation, but we question, which by the way, this is called your double adjacent. This will only be given with a full perm. Well, I mean, maybe in university you can do it without a full perm, or maybe somebody smarter than I can do it, but I'm going to only give these out with full permutation. So the double adjacent, we lock these two together, and then we just permeate these 5 things. So we find how many ways, which is 5, 4, 3, 2, 1. Now, also though, you've got 2 times 2s, because there's 2 switches here. So these are taking into consideration the number of places, and then you've got these little times 2s in here to take into consideration all your 2 switches. It could be A, B, B, A. It could be C, B, C, D, D, C. So, what do we got? 5 factorial times 4. Okay. B. Oh, right. This is where things get crazy. So the double adjacent is hard enough. Now, this is some other, more conceptual stuff. So A and B are adjacent, and C and D are not adjacent this time. So 1, 2, 3, 4, 5, 6, 7. So A, B are in here. Now, wait a second. How can I make the C and D not adjacent? Well, if I wanted to, I could have A, B in there and then have C and D there. But that not adjacent. That would be separated by exactly. It would be separated by exactly 1. So I could find them separated by exactly. That would be what we call the direct method. But it isn't very easy. So I would rather do what is called the indirect method. Now, the indirect method is based off of some stuff that we did from Venn diagrams. So, in order to find the not case, because I want them not adjacent, what I'm going to do is I'm going to take them adjacent and subtract them from the universe. What? Okay, here's what. In order to do this, I want to find the not case, right? Remember what the not case looked like in a Venn diagram? It looked like this. So in order to do not this, what I'm going to do is I'm going to take this, the universe, so this block, and I'm going to subtract this, the yes case. Not A, B, and C, D, I'm going to subtract it from the universe. Now, the other trick to this, though, is that the universe in this case, so A, B are adjacent and C, D is not adjacent. The universe in this case is A, B adjacent. the yes case is AB adjacent and CD adjacent. And then that will give me the AB and CD not adjacent. So this is a little bit tricky, but that's how it works. So all of them have to be dealing with the AB adjacent. Okay, now, hopefully that made sense. That is some pretty conceptual stuff. So, but I'm going the not case by subtracting the yes case. Okay, and I better hurry up because I'm at 11 minutes. Okay, so what I have to do is find this universe. AB is the universe, so I'm just going to find all the cases where AB are adjacent. So I drop the AB. I now have 5, 4, 3, 2. This is 6 because there's 6 places, and you can actually check there's 6 places this time, or just like we learned over here, when it's a full perm, you can just permeate all these things by locking these together. I still have to multiply times. This is the universe here. So the universe ends up being 6 factorial times 2. The AND case, the both adjacent, was 5 factorial times 4. So subtract those. So this is going to equal, so our final answer is 2 minus 5 factorial times 4. And if your teacher doesn't think that that answer is good enough, factor out the 5 factorial from both of these. See the 5 factorial in there? It's 6 times 5 factorial, and then that would give you 6 times 2 minus 4. So the factorial, which is 12 minus 4. So that would really be 5 factorial times 8, but I'm pretty sure they won't ask you to do that. This answer should be good enough. Okay, 2.5 minutes to do C. A and B are adjacent, B and C are not adjacent. Okay, so I'm going to use the same principle. I've already figured out the A and B adjacent, so now what I have to figure out is 5, 6, 7. I'm going to solve for when A, B, and BC are all adjacent. Notice what happens, though, is that B's got to be in the middle. In order for A and B to be adjacent and BC to be adjacent, now I know they asked me for not, but I'm going to... And then A is going to be there and C is going to be there, or there could be a switch, but I'm just going to join this whole thing together. I'm going to look for this threesome here. Now, after I drop these 3 letters A, B, C, I have 4, 3, 2, 1 left. There are 5 places this can be in, and I'm only going to times by 2 for the switch, because B has to be in the middle. The only switch I can do is that it could be CBA instead of ABC. They could be in 5 places. So this is going to be the yes case. So to get the not case again, I'm going to take my universe, which was starting with AB, which was AB adjacent. So 6 factorial times 2, and I'm going to subtract this new one that I, which is 5 factorial times 2. So again, this answer should be good enough. If it really wants you to factor that out. Now, maybe I'll go over that. Did you guys realize that 6 is 6, 5, 4, 3, 2, 1? So 6 times 5 factorial times 2 factorial. I can split this into that. That's what I did over here. Minus 5 factorial times 2. And then I can common factor this out. So 5 factorial, and then I get 6 times 2 minus 2, because that factored out of those. So then I get 12 minus 2 is 10. So you get 5 factorial times 10. Now, you probably don't have to do this, but that is, well, that's a simpler answer than that, but I'm sure this is good enough. Whew! Those questions are beast. That is an important principle to know, though. Whew, good thing I split this video. This one took me 15 minutes, too. See ya.